Hello, so today we are doing this problem from the context that just happened today. And so the problem says we have, it's called tree diameter, and the problem says we get an undirected tree and we want to return its diameter. And the number of edges, the goal basically of this is to return the diameter, which is basically just the number of edges in a longest path in that tree that we have as input. And so the tree is given as an array of edges, so such that we have uv is a bidirectional edge between u and v. And the nodes are just from 0 to the length of the edges. So it starts from 0 and we have 1 and 2. This is for the case where we have two edges from 0 to 1 and from 0 to 2. And the longest path has two edges because it goes from 1 to 0, that's one edge, and then from 0 to 2. So it's two edges from 1 to 0 to 2. And the other example is this one, where the edges are from 0 to 5, and we have the tree in this shape here because of these edges. And the longest path is to go from 3 to 2 to 1 to 4 to 5. And so it's a tree, but the longest path kind of goes from one edge all the way and passes maybe through the root and then goes all the way to another node, right? To another leaf node. So let's see how we can implement this. So okay, so let's see how can we solve this problem. So let's take the example where we have that is a little bit more complicated in the second example basically, and that was having something like a tree like this, where we have something like this, 1, 2, and 3, and then 4 this way, and then after that we have 5 this way. So if you look at this one, the longest diameter is of length 4, because it goes from here to like this, and then this one, and then this one. 1, 2, 3, 4. So it has length 4. So you can see here it went from a leaf all the way to the root and then back to the nether leaf, right? And so the general algorithm for a diameter, tree diameter, or you could just, like, even if you thought about it, you can come up with it, which is just you need to pick, let's just pick a random node, and then go as far as we can, right? And record the farthest node, and then do another DFS from that node to the furthest node from that one, and then pick that length, right? So basically pick a random node. In our case, we can just pick the 0, right? So this basically is using DFS. Run DFS to get the furthest node from, so let's call this node that we pick U, right? From U, let's call that furthest, and then run DFS from furthest, and find, or actually furthest will confuse things a little bit for us, so let's just call this V, and find the furthest node from it. W, and basically the diameter would be length of the path from V, length of the longest path from V to W. Right? So one thing though we need to be careful of, since this is an undirected graph, is if we came from 2, right, and went to 1, and from 1 we want to go to the neighbors, we should go to 0, we should go to 4, but we should not go to 2. So we need, in our DFS, we need to pass, of course, the node we are starting from, but the parent. so that when we are checking neighbors, we can check that the neighbor is different than the parents to not go back to the parent, because if at 1 we go back to 2, and then we will just keep recursing, right? Because then we will go back to, then we'll go to 2, and then we'll go to 1 again, and then go to 2 again, and then go to 1 again, and so we would have an infinite loop. We don't want to do that. And so this is the general template. And so first we get a list of edges. So first we need to construct the graph. Just the template of our final solution would be like this. So construct a graph. Of course, it's an undirected graph here. I will do that in detail later. And then once we have the graph, we can just start the DFS from. First, we need to have some kind of a best thing to keep track of the best solution, or basically to keep track, to know which node is the furthest, right? And so the first element will represent the length. So for our best, we would have the first element representing the length of the path, and then the other element would be just the node, like the last node in that path. Sorry, actually not the last node, just the node we start from. And so that would be for us would be -1, and we don't know which node it is, right? We don't know yet. So we'll just put -1. And then after that we will run DFS to find the furthest. So we will run a DFS from any random node. We're just going to pick 0 all the time, and 0 doesn't have any a parent, because we know in the problem it says that we start from 0, right? So we know that 0 doesn't have any parent. And then we need to pass the length so far, which at the start the length is 0, right? And with that, in our best, we will put the furthest. So sorry, this is actually the furthest node from the start node. Pass it to DFS. So we would have the first value is the length of the furthest, the length of the distance from the start of the DFS to the furthest node, and the furthest node we will put that in node. And so DFS will fill for us this best array here. And so to get the furthest node, which in our case here is just V, right? So V would be just taking best and taking the value here, node, so at 1. And so we would run DFS again from the furthest node, so from V. What is the parent? V is the furthest node. That means it's an edge, right? That means it's a leaf node, right? So it doesn't have a parent. And then we need to pass the length, and that's 0 as a start, and this will return us the furthest path from that V all the way until the furthest node from it, and the length of that distance, and that's the distance is the diameter we are looking for. And so we could just return, and that length, which is just the value in best at position 0, right? So we take a random node. It best works here if we take one that doesn't have a parent, a leaf node. So since we know 0 is a leaf node, we take 0 and we find the furthest node from it. So here the furthest node would be 1, 2, 3, 1, 2, 3. So either 3 or 5. Let's say we took 3. Then we will run 3. We will run the DFS again from 3 to find the furthest node from 3, and that's 5, right? And so when we find 5, the length of that is the diameter. And so that's pretty much the algorithm for finding the tree diameter. Now, how can we do our DFS? It's just your usual DFS with the caveat that I explained here, that we need, since it's an undirected graph, we need to not go through the parent again. And so let's write our DFS here. So we are passing the node, let's call it u, and we are passing the parent, and we are passing the length of the path. And so we want to keep finding the best path to the furthest node so far, right? And since we go through with DFS, we will run it for each neighbor, and so we will just need to say best is equal to the max of best. So with Python, since the length is the first value, then it will take the max using that length. So that way we will get the furthest node, right? And the node here is just the whatever is passed as the start. And then for neighbor, so we'll go through all the neighbors of u, right, of the node, just normal DFS, and then we will do our check here to make sure we are not going through the parent again. And after that we will run DFS again. The first element parameter is the neighbor, and then what is the parent of this neighbor? It's u, right? So we go from u, we go through its neighbors, so it's the parent. And we will need the length. The length increases by 1 since we are going through another edge, right? And using this best, we will pick the furthest from these nodes. And that's pretty much it. So let's code this up in Leetcode and see if it passes. Okay, so now let's run. Let's just write the algorithm we just saw. And so the first thing we need to do is so we need to construct the graph, right? So I'm just going to say default dict list. This just avoids for me having to check if an element is already in the graph and then having to create a list for it. Just by default, any element would have an empty list. And then we need to go through the edges that we have as input. And since it's an undirected graph, then u would have as a new neighbor v, and v would have as a new neighbor u, right? And after that, we will just declare our best variable that will find for us the furthest node from 0, which is the node that we are picking here as the node that we will start from. And so this would be, we'll start this out as, okay, let's just put it here. So we'll start our best. We don't know the best, the furthest node from 0 yet, so let's just put -1 as the length and -1 as the node. Since those values don't exist, and then start the DFS from 0 to find the furthest node from 0, and the length starts out as 0. So this is to find the furthest node from 0, right? And we pick 0 as the start node. And then the furthest from 0 would be, DFS will put it in the second position, right? So here best would be length. Furthest node from start, right? From DFS start. And then we will run DFS again. And so we need to just reinitialize our best array to give us a new value. Because if this is still the older value, then the max maybe is just that, right? And so we'll do DFS starting from the furthest node we just found. What is its parent? Since it's a leave node, it does. We can just leave the parent as empty since we haven't started our DFS yet, and the length is 0. And we will find with this the furthest node from this furthest node from 0. This is a bit of a mouthful, but it's just we find the furthest from 0, and from there we find the furthest from that node, and that length is what we are looking for. And since that length is what we are looking for, so we'll just return it as the length is in the first position, right? And so we just say best 0. And now we need to write our DFS, which gets the start node and then gets the the parent and the length. And at each step of BFS, we will just check if we have a new best or new furthest node. And so this would be length and u. And the Python will basically take the max using the first value, which is length here. And then we'll do normal DFS, which is checking all the neighbors. So the neighbors of u. And here, just to prevent going back to the parent, which would give us an infinite loop or a recursion that doesn't terminate, we'll check that it's not the parent. And if it's not, we'll do a DFS again from the neighbor to the node. From the neighbor and the parent is u, right? And then we would have the length increased by 1 because we just went to a neighbor, right? And that's pretty much it. So let's run this and see. Okay, so that solution passes. Okay, so what is the time complexity for this solution? And so let's just say, so since we know, let's call the length of edges n, right? Just to have something to write the time complexity with. So if this is n, then that means that this constructing the graph here would be O of n time, right? And then that means that DFS here would at most traverse n edges, right? Because it won't do more than the number of edges, right? Because we just go through each edge once and we don't go back to the parent, right? So this DFS also is O of n. And same thing for this DFS, since the same reason, the same logic applies. So overall we have like O of n plus O of n plus O of n. Also DFS is usually O of v plus e, and that's the number of nodes, which the problem says is just from 0 to the length of the edges, so it's O of n. And the number of edges is the length of edges, so it's O of n also. So this is O of 2n. So both our DFSs are O of 2n, and this is O of n. So overall our time complexity is just O of n. Now what is our space complexity here? So space complexity here, we are just using this extra graph that will contain at most O of n also, like, right, the number of nodes. And so space complexity is also O of n. Okay, so now let's see how we can solve this using BFS. So the idea with the BFS solution, so first let's just draw the tree. So we have 0 here, and 2, and 4, and then 5, and 3. So the idea of BFS is that if we take the first level, so BFS we do level by level, right? So we do first level, then the second level, and then the third level, right? So if we have a tree with multiple things like this, if we can just find the last level, right? So the number of levels in that entire tree, right? So this would be the diameter, right? From this level. So this level counts, this counts as a level, this counts as a level, this counts as a level. So if we find the count of all these levels, that would be the result, right? And so to do that, what we can do is first take all the leaves as in a level. So these are the leaves. So level, start the level, so the first level contains leaves only. And then from there, just start exploring the elements next to it in a BFS fashion, right? So that would mean we would find this, we would find this for this 5, and this one is a level, and this one is a level. So we'll find the entire, so we'll find the number of levels. And if we find the number of levels, then we could just say -1. Why -1? Because the leaf counts as a level, but the edges, so if you count the leaves, we'd have 1 level, 2 level, 3 level, 4 level, 5 levels, right? But 1, 2, 3, 4, we have just 4 edges, right? If you have, like, let's say this, you have 1 edge but 2 nodes. If we have this, you have 2 edges but 3 nodes, right? So it's always -1. So levels -1 is what we are going to return. So that's the idea. Now, how would we code that, right? So we would first construct the graph, right, in the same way that we did with DFS. And then after that, we will level starts out as 0, right? And then we'll start our current level, right, where we would put get leaves. And then after that, we will say, and then from there, just continue to do normal BFS, right? And so that would mean doing while current level. We will start the next level, right? So normal BFS usually uses 1 queue to do this, but since we want to count the number of levels, we are going to do it level by level, right? And so we will start out the next level. And I'm just using set here to not get duplicate values, right? Duplicate nodes, because it's an undirected graph. I may have a node appear multiple times. And then I will go through the current level to get all the nodes in the next level by just getting the neighbors of each node in the current level. And so that would mean you and the pre or the parent or whatever. So you have a node here, and then this one, let's call it pre. This is basically to do the same thing as we did in DFS to avoid going through the parent one more time, right? And then this is in the current level. And what we want to do is go through the neighbors of each node in the current level. So that would mean like this, go through the neighbors of the node in the current level. And so we know pre is the parent of u, right? So what we will put in the current level is in the format like this. So we'll put in the current level nodes of the format node and parent. And since the leaves don't have parents, we will put just node and none, right? And so for the neighbors of the vertex in the current level, we will check first to make sure none of them is the parent of the node, because otherwise we will just go back and not finish. If it is, sorry, this is neighbor. So to be more clear, let's just name this parent. Let's just call this parent. And then if neighbor is different than parent, then add it to the next level. And so adding it to next level means just take the next level and add that neighbor. And now once we are done, since we want to process the next level and the while loop checks the current level, we'll make the next level that we just filled up. Since we finished all the content of the current level, we can override it now with the next level. And then we increase our levels count. Let's call it here levels equal to 0, since we know that we just finished one level and we are going to the next level. So we'll say we have a new level. And then once we are done and we processed the entire tree or graph, we can just return levels -1 for the same argument that I just mentioned, which is if we have 2 nodes, this is 2 levels, but we have 1 edge, right? And just to avoid if a tree has just one element, right? So the longest path is 0, right? But the level is 1, and so we'd have -1. And to avoid that, we'll just say max of this and 0. And that's pretty much the algorithm here. So let's just code it up on Leetcode and make sure it passes. Okay, so now let's code the BFS solution. So first we need to do the same thing we did before, which is construct the graph in the same way we did with the BFS. Okay, I'm just going to copy paste it. So just going through the nodes. Yeah, I'm just going to make it set to avoid duplicates here. And then we are going to create the leaves, right? Remember, and put them in the current level. So this just get the leaves. And to get the leaves, what we are going to do is just, so each leaves we'll consider first that it has no parent, right? And then for every node and its neighbors, which are in a list, right? In the graph, right? We'll take those that have length, the neighbors of length 1, because that's what an edge would be, what a leaf would be, right? So if you look at the if we look at the example here, a leaf like 1 and 2, they have one neighbor each. Same thing here, 3 has one neighbor, 5 has one neighbor. And once we get that, we will start start our BFS, right? So current level, we'll start the next level array or a set here, and then for u and its parent in the current level, so we'll go through each node in the current level, get its direct neighbors so that we can start the next level. And so for each one of them, take its neighbor, and to avoid loops, let's just make sure that it's not the previous one, or not, it's not the parent of the node. So this is neighbor. If it's not the parent, then add it to the next level so that we can explore it next and count this as a new level. So it would have the neighbor and its parent. What is the parent of the neighbor? That's u. And then that's the node u. And then after that, for the current level becomes the next level, right? And we need to increase the count of our levels. So let's just initialize levels here and increase the count since we have a new level. And at the end we need to return levels -1 for the same argument I just said in the explanation. And then just to avoid having -1, we'll max this with 0, and that's pretty much it. The BFS solution is just this. Let's run this. Neighbors. So that should be add. Okay, let's submit. Okay, so this solution also passes. Okay, so what is the time complexity of this BFS solution? So we know that usual BFS time complexity is O of V plus E, right? The number of nodes and the number of edges. And for the same arguments as we mentioned in the DFS solution, this is n, so that would be O, this is O of 2n, right? So it's O of n. Now, the only thing that we are doing different here is checking the leaves, all the leaves first, right? And this, you can see it's traversing just the graph, right? So it's just O of n at most. And so we would have, so we have another O of n here for that. And so overall, it's just O of n, our time complexity. Now, what is our space complexity, right? So same thing, we have the graph here that takes O of n, and the levels here will take O of n at most, so overall it's O of n. Okay, so that's it for this problem. We saw two solutions, one using DFS and another one using BFS. There are different other solutions that you can look at, but those are the two that the most important to know. Yeah, so thanks for watching and see you next time.